SwayamPrabha. Digital India. Educated India.
Welcome to Module 5. Module 5 we will cover urban growth, land suitability, accessibility and land price. And in lecture 21 we are going to start with urban growth assessment. The different concepts that would be covered in this lecture are urban growth and transformation process, Landsat satellite data, land cover classification using satellite image processing, urban transition and urban growth pattern. In the last lecture or in the last module, we have covered population growth and transformation. So, in this particular lecture, we will focus more on the urban growth, of course, the growth of the urban area and its transformation process. So, if you remember from previous lectures, we have discussed transformation process in terms of land use, location, land price and so on. For example, we have talked about the different types of land use, we have talked about the location choice of individuals, like people choose a particular locations to live or a company decides to choose a certain location to locate its offices and so on, and of course land price also change in an urban area. So, all these transformation processes has got land involved in it. So, land is the fundamental part of this transformation process. So, we also explained in previous lectures different theories, for example, the economic theories of land price and location choice, where we have talked about how land prices depends on land quality as was suggested by Ricardo in 1817. Then we have talked about land use patterns and land prices and how it depends on distance and transport cost, which was suggested by von Thunen. And then we have also looked into Allen's bid rent theory of land use, how rent changes at different distances from the central CBD or from a central part of the city. And we have also talked about discrete choice models for predicting choices between different alternatives. These choices could be for different locations. And then we have also talked about the spatial interaction theory of land use, where we have shown a gravity model equation and how location and distribution of jobs and residences could be predicted using this kind of model. And we have also talked about accessibility based location models, where accessibility plays a big role in determining how a person chooses a particular location and so on. So, these are the theories which helps us to determine what sort of transformation or what are the background processes or what is the fundamental reasons these transformations happen within an urban area. But again, we are talking about when we have a distinct urban area, we have a urban area with a certain boundary, and within that boundary what kind of changes are happening, that is being described by these particular theories. And we have several models accompanying these theories. For example, the theory gives us the basic understanding, whereas models helps us to actually compute that what kind of change could be expected in future, or what kind of change is taking place, what is the change in different components or different amongst the different agents. For example, individual agent in an urban area, similarly a company may be an agent in an urban area and so on, or real estate developer could be an agent. So, how these agents are going through changes, and that is leading to the overall change in an urban area. So, we have talked about agent based simulations, we have talked about rule based simulations, we have talked about micro simulations. So, these are the things that we have discussed, and we within the broad framework of land use transportation model and even activity based model, we can determine how a urban area would going to transform over a period of time. But still urban area, the area is not fixed, the area also gradually expands, or there are certain patterns in how a area grows or an urban area grows over time. So, that is also very important for an urban planner to understand before he can undertake the land use transportation modeling process. So, similar to population growth and its transformation over a period of time, urban area doesn't only gets transformed within itself, it also expands. Municipal boundaries, municipal areas expand their boundaries by taking in more maybe rural areas from the adjoining areas, or this by agglomerating some surrounding areas. So this is the this process of taking or expansion. This also needs to be understood, and that is what we will cover in this particular lecture. So along with this total amount of expansion that is happening for an urban area, or in which direction the expansion is happening, we also need to assess the urban growth pattern. This helps us in monitoring the urbanization process and also its ecological impact. For example, we have heard of the term called sprawl, and what it means is suburban development. It's a phenomena primarily observed in the developed countries, where people have shifted away from the central core city area to surrounding neighborhoods, which are distinctly separate from the urban core or the urban area, and people need to travel quite a bit to access those areas, but you get a better quality environment in those areas, but at the same time this increases the travel cost, it increases the cost of the resources that or infrastructure that you need to lay in those areas. So this kind of development, that means this pattern of development definitely has a impact on the ecological on the environment, or has got an ecological impact. So we need to talk about the expansion of existing and development of new urban areas, which is required to accommodate the growing population. So that means we need to think about which areas to acquire, in which direction the municipal boundary can expand. This needs to be looked into, and while we do that, this may lead to loss of good quality agricultural land, or it may lead to deforestation, or it may lead to loss of biodiversity. That means if I keep on expanding the municipal boundaries without any other consideration, then it may have some bad impacts. So this could result in loss of agricultural land, loss of forest, loss of biodiversity, and so on. And this kind of change could be traced or measured through land use, land cover change processes. And this similarly, what it means is we need to understand how the land cover is changing. For example, gradually there is increase in the built up area in a certain region, in which direction the built up area is increasing, and what is the quantity of that built up area, and so on. So similarly, inappropriate selection of land area may also lead to higher energy consumption, air pollution, scarcity of water, flooding, public health issues, urban heat islands, and so on. So we also need to perform sort of land suitability analysis, which we will take up in the next lecture in details. But land suitability, and also to determine which areas to be selected for future urban growth, this all goes hand in hand. So we need to understand that which are the areas we should gradually bring into our urban area. So this selection process is important, or we need to identify appropriate areas for appropriate type of uses. For example, we need to determine uses for a solid waste landfill site, or we need to determine suitable areas for industries or for a particular urban area, and so on. And LUCC monitoring, or land use cover change monitoring, is usually undertaken using remote sensing images, and particularly Landsat images. So Landsat is a satellite sent by the US government, and so these images are available for analysis, and this could be utilized for land use, land cover monitoring. And we need to analyze these remote sensing images to get proper estimates of or to quantify how much amount the urban area has expanded, and so on. So which cannot be done through normal maps, or it will be difficult to do through normal maps. So for example, I am showing you the using Google Maps. I am showing you images of a satellite image of Kolkata for the year 1998. As you can see, the green boundary over here, this is the boundary of Kolkata Municipal Corporation, and this red boundary is the Kolkata metropolitan area boundary, which is pretty big. And as you can see, these gray areas that you can see over here, this is the extent of built up area for Kolkata. This is the Kolkata, and then this part is Salt Lake, which is called Bidhannagar Municipal Corporation, and then there are also areas which are developed beyond this. So, if you see this map, we can see definitely that over here development is intense, but beyond that development is gradually the intensity is lessening, and then we have green areas. Similarly, if I take a look at for the maps of 2008, we can see that development has expanded. You can see that these areas we have previously the intensity of development was not there, but it has expanded over here, and then in 2018 we can see further expansion over here. So, we can, using this sort of images, we can of course understand in which direction the growth is happening or to what extent development intensity is changing, but we can make only qualitative assessments. So, to do quantitative assessments we need to do something more. So, that is where satellite images comes in, and first I will explain the basic characteristics of satellite image. Like I already explained that Landsat satellite data is used for agricultural land cover classifications. It could be used for land cover classifications and monitoring at both regional and global scale. It could be used for forest monitoring. It could be used for urban land use classification or used for urban land use and land cover change detection. So, these are the things how the Landsat data could be utilized, and Landsat is basically a series of satellites. Landsat 4 and 5 is currently now it has been deactivated, and currently we have Landsat 8, but we still use images from Landsat 4 and 5 because we require to analyze data from previous years. And so, here we say that the sensor that is on board, we call it Landsat thematic mapper, and this we call TM data, and these images have got 7 spectral bands. The resolution is around 30 meters, that means 1 pixel covers around 30 meters, and we have got band 1 to 5 and then band 7, which has got a resolution of 30 meters. We have got an infrared band, thermal infrared band, which is band 6, and here the resolution is 120 meter, but it is resampled to 30 meter pixels as well, so that we can use those data as along with the other data sets as well. So, this is the how the satellite data characteristics are there. So, we have got many layers of data in form of different bands inside satellite images, and each one shows different types of it covers different wavelengths, and accordingly we can capture different information. So, Landsat 8 is an updated is a newer version of the satellite, where we have got operational land imager and thermal infrared sensors, TIRS. It has got 9 spectral bands and 2 thermal bands, and it also has got a panchromatic band, which is band number 8, and here the resolution is 15 meter for each pixel. So, here we summarize the different bands that are available, bands 1 to 11. So, in the Landsat 8 there are 11 bands, in Landsat 4 and 5 there is around 7 bands. So, these are the wavelengths which is given in micrometers, and around 0.43 to 0.45 this is coastal aerosol. We can measure that, then 0.45 to 0.51 this is the blue component of light, 0.53 to 0.59 green component, 0.64 to 0.67 red, then 0.85 to 0.88 near infrared, and so on. So, shortwave infrared, and then panchromatic data over here. So, at different bands we capture different kinds of information. So, what we can do is using this different band data, we can combine this different band data to create composite or multispectral images, and we call them composite images. We sometimes we can also call them false color composite. In this particular case, we have used NIR, near infrared, red and green band to create this kind of images, which looks different from the standard images that we see in Google Maps. So, this is again from Landsat satellite images, and this false color composite data for urban areas, and here we use near infrared bands, and when we use near infrared bands, it increases spectral separation, and it can create maps where urban land cover can be interpreted more accurately. Like we were seeing that when we are seeing the Google Map images, we cannot distinctly identify where the built up area is ending and where vegetation is also starting, or where the vegetation and built up area how it is mixed. But if I use infrared bands, then we can more accurately classify this kind of conditions, and that is why we require these false color images which represent multispectral images to determine what are the different kinds of develop or what kind of development has happened at different pixels. In this case, of course, 30 meter pixels, because each pixel represent spectral resolution is 30 meters. So that's why we can see over here in these images, this red indicates vegetation, these ones are vegetation, greenish this part indicates developed area, and black indicates water bodies. So this is an example of a false color composite image, and you can see how for this data sets for 1998, 2008 and 2018 for Kolkata Municipal Corporation area. So we can see that gradually the intensity of development over here, this has got intensified and this has further expanded in future years in 2018. But as you can understand, the impact from the change from 1998 to 2008 is significant, whereas from 2008 to 2018 that change is not that significant. Maybe some changes in those areas, we can see some intensification maybe, but not in all areas. So based on the image that you have seen, we were explaining the image in qualitative way, but if I want to quantify the amount of growth in a urban area, or what kind of growth, what kind of development is happening, we need to do land cover classification and using image processing, which is satellite image processing. So that means we need to quantify the amount of change that is happening. So in supervised classification, or when we do satellite image processing, we can do both supervised and unsupervised classification. I will explain supervised classification. What it means is, each pixel of the image is assigned a user defined class. A class, maybe it's a kind of land use we can say, or land cover we can say. So like water, vegetation, built up area, these are the three classes that we are defining in our example. And if I can assign each pixels to each one of this class and then use an algorithm to classify based on my selection, or based on my based on some examples that I give to the software, the algorithm can classify the different pixels of an image into different classes. So sometimes 3 classes may not be enough. We may need to do more 4 or 6 classes, or even more than that, based on what kind of what is the quality of the data and so on. But in this particular case, we have used an example where we are categorizing the pixel into only these 3 classes. So to do this, we have used the ArcGIS software, and where we can do image analysis to a certain extent, and we have to do raster data processing, because it's a satellite image is a raster image, and we are taking bands 4, 3, 2 of the satellite image, and then we are creating a new mosaic as per the boundary that for which we are working, and we are saving that in TIFF format. So TIFF is a data format, and first we get the actual raw data from the satellite image, we combine the bands, and then we create a new map out of that, or a new image out of that, and that is the new raster creation. And then we, within the ArcGIS software, which is a very, very popular GIS software, Geographic Information System software, there we open the toolbar where we open the extension module, which is called image classification extension. So we can see that this is the image classification extension module, and this is the image that we are working on, and this is again the extended Kolkata area. This is KMA area. This is not only Kolkata Municipal Corporation. We are seeing the river Hooghly going in between. So this is river Hooghly, and these are some of the wetlands. This is the East Kolkata wetlands, and this is the built up area, the core area of Kolkata Municipal Corporation. So So, once we have opened the extension for image classification, we select of course supervised classification, and we first need to train the algorithm. That means we need to do a training dataset collection, and we need to train the algorithm class by class. That means we have to show it what is water, what is vegetation, what is built up area from the image itself. So, for that we can either choose draw polygon or draw rectangle or draw circle, and in this case we have used a polygon, and we have selected from the map like this, and we have said this pixel is this polygon area is a water body. So, this is the first one, and similarly we can add another polygon also as a water body, and this would be the second one. In this way we will keep on adding that in this particular window, and you can see this is shown as class 1, class 2, class 3, class 4, each one is each different polygons. And then we can merge all these classes together, and we can say that these classes are all water bodies. That means when the algorithm will run, it will take this kind of pixels and convert and say that this would be a water body. And similarly we add for built up area, vegetation, and so on. And once we have done this, we save this data set, and then we can open again classification, where we choose the algorithm. Over here there are several algorithms which are possible. We have chosen the maximum likelihood classification algorithm, which is a very popular algorithm, and it may not be the most accurate, but it is one of the most popular algorithms. And then we open the data set again over here, like we have input the signature file, that is that data set, and then we can also say the output where this image the results will be shown, and then we can run the algorithm, and we can after that we can assign colors to the different classes, like we can assign a color to a water body, we can assign a color to built up area, and so on, and then we get our classified image. So, this is the result of our analysis, where we see that we have done the land cover classification for KMC, where red is built up area, and green is vegetation area, and blue is water body. And this is based on my choice. I can assign any kind of choice to these colors once the classification is done, but the classification is done by the algorithm which is inbuilt in the software. And over here we can see that the pattern of development, and as you can see, unlike the previous images, even the FCC image or the Google image, this image is very clear and very distinct, where we can identify exactly where growth has taken place. And this is the area where in 1998 this was the extent of built up area, this was the extent of vegetation. This vegetation could be because, and we can see also sporadic development surrounding this. So, this is a kind of pattern of development, like for example, there are some green areas in between, these are maybe parks and all, whereas over here the green area could be agricultural field, or it could be normal vegetation in neighborhoods, but the neighborhood is very sparsely developed or low density neighborhood. So, and over here we can understand, because of water bodies, this area must be a wetland. So, in 2008 we are seeing urban transition happening, we are seeing the development is intensifying, and we can also measuring the pixels over in our image also, we can measure exactly how much amount of development has taken place in terms of, because it is a geographic information system, and we can also there is a coordinate attached to this data, we can exactly measure how many square kilometers of area has been developed during this 10-year periods. Similarly, in the year 2018, we can see this is the map where we can see built up area, vegetation, then water bodies, and then what we can do is we can overlay, we have overlaid all these three maps together, like 1998, which is shown in gray, then 2008, which is shown in orange, and 2018, which is shown in red. So, this gives us an idea about how the transformation is taking place, and also it tells us where the direction of growth is happening, and how the direction of growth has changed even during the different these 2 decades. For example, 1998 to 2008, growth was in this particular direction mostly, but because there is wetlands, this side is the river and this side is the wetlands. So, growth is not possible in this particular direction. So what happened? So growth has got restricted, and during the year 2018, growth has started again taking place in the southwards direction. So these are the direction of growth that we can ascertain from this kind of analysis. Similarly, we can also understand the constraints of growth. Like I told, that this side is river, so no growth is possible in this side. But again, some development happened along this particular river bank, where some new real estate development projects are coming up. And we can say that this area, there was because of water wetlands, the growth is not taking place. So we can also understand the constraints of growth. Similarly, quantity of growth we can determine by measuring the amount of area under different land uses or land cover, and from there we can do a quantitative analysis, and we can have a broad understanding of the urban transition. And if I know other information regarding some other sensitive areas, like okay, this area is very good agricultural land, or there is a forest in this area, we can also understand the likely environmental impact because of this kind of urban transition. So now summarizing for this two decades, 1998 to 2008 and then again 2008 to 2018, we can see that vegetation has reduced from 74.7 square kilometers to 61.3 square kilometers, and then from 61.3 square kilometers to 60.8 square kilometers, and water body has reduced from 7.48 to 6.2 in 2018. In between we are seeing 7.66. This sometimes little variations may occur in the image classification based on the amount, type of classes, the kind of accuracy we have, what kind of steps we have taken during the training. Because this is an example, we have done it not in that details, maybe some amount of error has crept in. But this also indicates that on that particular date when this image was taken, probably there may have been rainfall which may have shown more amount of water body in different areas. So that could also be possible. So that means more or less there is not change in the water body from 1998 to 2008, but we are seeing as reduction in the water body from 2008 to 2018. Particularly, there may have been some encroachments in the area over in this side where there was wetlands. So that's maybe one of the reason for water body reduction. And then we have got built up area which has increased from 119 square kilometers to 132 square kilometers. And then we have seen that from 2008 to 2018 there has been very little change, where we have seen only 134.28 square kilometers. That means like only 2 square kilometers of built up area is increased. So that means growth is stalling in the this particular urban area or this municipal corporation. But as we understand that this is part of a larger KMA, Kolkata metropolitan area. So growth may have happened in the surrounding municipalities over here. Like for example, we have got Salt Lake municipality over here, then we have Newtown over here. So a lot of development has come up in this particular areas. So this so growth may have been taking place over here, but because we are in this image we are showing only KMC boundary, so that's why it is not that clear, but we can understand some growth is also taking place in this direction. So once we have understood the amount of growth that is happening in different directions, and also what kind of transition is happening, change in the built up area and so on, then we also need to understand what kind of growth pattern that is being observed. So unlike the qualitative categorization like sprawl or compact development, because we loosely call okay there is sprawl kind of development or compact development, but we also need to quantify the kind of growth pattern that is taking place. For example, 3 kinds of growth pattern has been quantified based on Landsat imagery in the works of Hopfine and Wilson, and this work has been used by many other researchers as well, and they have quantified growth in form of infill growth, expansion growth and outlying growth, and further outlying growth could be classified as isolated, linear branch and clustered branch. So these are the different kind of patterns that could be observed in an urban area, and this gives us lot of other seeing these patterns we can decide on ways of future growth or how we can control future growth and so on. So, this classification system depends on the relation of the new area with the existing developed area. That means, we have existing developed a built up area, and then new development happens around it or within it or maybe further away from it. So, accordingly we will decide on what kind of growth it is, but it is all based on the assessment of the existing area. That means, if existing area is here, then only we can say it is happening, new growth is happening inside or adjoining it or outside it and so on. So, but one thing we have to be very careful is, even though we can draw certain conclusions from this kind of analysis, but we have to understand that satellite imagery analysis is incapable of explaining spatial temporal details. That means, what kind of change happens in the spatial area in different temporal periods, until unless we have got satellite images from different temporal periods, which I showed you in the last slide. And then urban pattern dynamics and urban growth processes and its environmental impact are difficult to predict from this kind of analysis. So, we need to do other analysis, like for example, we need to do those models that we talked about at the beginning, so to understand what kind of transformation is happening, but certain amount of information could be available from this kind of analysis. So, how do we quantify? As you can see, this one is infill development, black is old urban patch, gray is newly developed urban patch. So, this one is gray is the newly area which is growing inside, and this has been as per the Hoffine-Wilson study, this kind of development is called infill development, where the development has happened inside. Then edge expansion or expansion, as we can see that we have the old area and the new area has happened adjoining it, and then we have the outlying growth, which is we have got this newly developed areas which are far away from the existing old urban patch. So, as you can see from the image itself, we deal with pixels. So, depending on pixels we determine the quantification criteria. So, in this particular case, a roving window method has been used. That means, a window is being we are taking one window at a time, and as per the size of the window also the results will vary, and each pixel is analyzed according to its neighboring pixel or surrounding landscape. So, that means, we take one pixel and measure how it is related with the surrounding area. For example, this particular pixel, it has got new area, old area on 60% of its surroundings, whereas the other 40% may be new area, or it could be just the reverse. That means, this side there may be 40%, this side there may be 60%. So, this kind of pixel wise analysis we need to do. Results vary as per window size. Of course, depending on the size of the window it will change. Then ratio of length, Zhu et al. Has this was the method given by Wilson, Hoffine and Wilson, and then Zhu et al. Has given another method where ratio of length of the common edge between these two developments, this is the common edge, to the entire patch, the total patch of development. Also considering a relative, which is basically a relatively homogeneous area different from its surroundings. Depending on the ratio between the common edge and the patch perimeter, we determine what kind of development it is. So, as discussed earlier, there are three broad kinds of development. For example, in infill development, a non-development pixel is converted into urban use, and it is surrounded by at least 40% existing developed pixels or urban area with public facilities such as sewer, water and road. That means, development has happened within, and within means at least 40% of existing developed pixels, surrounding pixels, 40% is existing area. So, that is the least amount. Of course, it could be more than that. And we can say that development of vacant land in already built up areas, this could be quantified as infill development. Then brownfield redevelopment of old industrial sites, rail yards, or repurposing sites which has lost economic significance. So, this could be also called infill development. And then in expansion, this is also referred as urban fringe development, and here development of a pixel while surrounded by less than 40% of existing developed pixels. So, this is just the opposite of that. This is at least 40% and this is less than 40%. That means it has to be less than 40%, then only we can call it an expansion and not an infill development. And this is also referred to as edge development, and that is unidirectional spreading parallel along an edge. So, this is an edge, and so it is a unidirectional spreading parallel to this edge is also called expansion development. And this explanation was given by Foreman in 1995. So, then comes outlying development, which is newly developed areas which are distributed at relatively larger distances from existing developed areas. So, this is not expansion, that means development is quite far away from existing development. So, for example, in this particular image, you can red indicates existing built up area. So, this red is the existing built up area. Blue is infill development. So, in between maybe some brown fields, some empty plots are getting developed. Then green is extension development. That means this at the edges of the city new growth is happening. So, this is extension development. And then we have isolated growth, which is a kind of outlying growth where non-developed pixels are developed at little distance from the existing developed area. And Foreman also defined it as perforation of habitat or land type. What it means is this is my expansion, but sometimes people may not exactly develop as a from the just exactly over here as in case of expansion. They may just develop a little bit away based on availability of land, based on land price and so on. So, and or based on certain other geographic features as well. So, if this kind of development is happening in the urban area, then we can call it a isolated growth development, where it is near to the main development, but it is still separate. Then linear growth is when new developed pixels are connected in a linear fashion along a road or corridor, and this could be also referred as ribbon development. That means we have got suppose a metro corridor like this, and because the metro corridor has come, growth has started taking place along this metro corridor, and the urban area starts expanding in a linear way along this corridor, and this is also called ribbon development. And then we have got a clustered branch kind of development, where usually a large and dense development cluster happens, which is far away from the main area, like over here, main urban area, and this is also known as leapfrog development. And this sprawl could be classified like this, or it could be an airport city development which is far away from the city, but it's still a big development which has taken place. So, these are all different kinds of outlying development. And in addition, we can also have TOD kind of development, that is we take up existing station areas, we develop them intensely. It's sort of an infill development, but we can also give it a separate category called TOD, because this is very, very important in today's context, transit oriented development. So, now after we have done this kind of, we have seen these three patterns. Now, if I take our previous images for Kolkata, the classified images that we have already developed for Kolkata municipal area, where we have taken the images for 1998 to 2008, this is a transition image, and then again from 2008 to 2018, we are seeing that within the area, this green part we can call it edge expansion, that is this area the growth has happened where the edge has expanded. Red is infill development, that means already built up area was there, and now new development, this red has got this red dots, this has happened over here, which is inside the urban area over here. See some white areas, some green areas are now converted into red. So, maybe some open areas or empty plots are now getting filled, and then outer growth is suddenly we find development over here or development over here, and in this particular image we are seeing that some amount of extension has happened over here, little bit, not too much, and then we are seeing little bit of outer growth over here. And because this area was already there, so this area's outer, this kind of expansion has happened. So, these are the three kinds of patterns we can identify in our classified image, and again this could be done in a more detailed manner as well. And what we can from this particular image, what we can summarize is we can determine the future growth pattern definitely, but at the same time we can also understand the total area required for expansion in future. So we know that from our previous discussion that suppose this particular urban area there is going to be experiencing migration and new land area would be required, and also for the natural growth of this particular urban of the population in that area we require new land. What amount of land area or how much the municipality has to expand, or is there a requirement for municipality to develop some new green fields? That means we have to take up some new agricultural lands. How much of it needs to be taken up? So if I analyze the past trends of future growth patterns, we can understand how much of growth is happening inside the city, within the built up area, within the existing urban boundary, and how much of growth is happening outside the city. So, and what are the amount of areas left inside the city where further growth can happen. So we can determine for this new population what kind of area is required. So how much new area has to be acquired, or in which direction the city should grow. So municipal boundary adjustment could be done based on this sort of analysis. So we would be able to understand how we can expand the area. So when we are undertaking a land use transportation plan, we first need to ascertain the boundaries for which we are going to develop the plan. So if we understand that 10 years down the line or 20 years down the line we require much more area and we need to undertake select some areas, then automatically we need to automatically what happens, we need to determine that okay, these are the direction in which the municipal area will grow, and we need to expand the municipal boundaries in those direction, and we say that land development or urbanization will take place, and accordingly based on this new boundary we have to do analysis of the existing as well as future condition or the future land use for that particular area. So for the existing analysis or the base year data set should be for this new boundary area that we think that will be required in future. So in addition to municipal boundary determination or adjustment, we also need to understand that okay, this kind of development can help us to develop the development control guidelines. That means if we are seeing that certain areas are being encroached, like over here there are wetlands, and if we see that some kind of development is happening which is not desired, then we can create some development control guidelines through which we can also control future development. So these are some sort of policies we can also frame to guide future development. So these are the references you can look at. And then to conclude, we can say that satellite image analysis is essential to estimate urban land cover classification and to quantify urban growth and direction over a time period. But while satellite image analysis can help us to understand urban growth in terms of its constraints, likely environmental impacts, etc., both in local and regional scale, over-reliance on this sort of analysis may lead to an incomplete understanding of the context of urban growth. So we need to have lot of more information to really understand why growth has taken place in a certain direction. But this satellite image analysis do give us lot of initial information, and also it can help us to quantify. And finally, urban growth pattern analysis is required to estimate and justify the need for municipal boundary adjustment and area expansion, which is the starting point of our land use transportation model. Thank you.